So looking at this problem, a big hint is that they put X and Y right on the picture. But even if you couldn't see that X and Y, you don't have your augmented reality, virtual reality goggles on. If you looked at this in real life, you would see that there's nothing curved, everything's horizontal and vertical. This makes sense that it would be a Cartesian coordinate problem. Okay, so first let's start with the crate. We'll get the free body diagram of the crate. So again, free body diagram, make a closed loop. Okay, draw everything in the loop only. And there was that string. Draw all the forces that are in the loop. So there's the weight of the crate. I'm going to say M crate times G. And then there is the tension that I cut through, all the forces you cut through. So I'm going to just say T for tension. And that equals, on the other side, you do mass times acceleration. And in this case, they tell you what the acceleration is. So it's kind of nice. It's the mass of the crate times A, which is the mass of the crate, times 6 meters per second squared. Okay, and you take X and Y components. There's obviously only Y components, so we'll do sum Fy equals MAY. Naturally, we'll take up as positive. You don't have to. So you get T minus M crate times G equals, going up, M crate times 6. And solving for T, you get M crate times 6 plus G. And the crate was 50 kilograms. Okay. G is 9.81 meters per second squared. You get an extra 6 meters per second squared. So there we go, 9.81 plus 6 times the 50 kilograms, 791 newtons. Okay, but what they really want are the reactions at A, like in a statics problem, and this now turns into a statics problem because the beam is not moving, only the crate's moving. So again, free body diagram, closed loop. Redraw only the things in the loop. So here's the beam was in the loop with this little pulley, this string, and this little piece of the string. Okay, that's what's in there. Put in whatever force is in the loop. They didn't give a mass for the beam. Let me go double check the problem and make sure that I didn't forget to write down the mass of the beam. Okay, so I read the problem statement several times and the beam weight is not mentioned. I did some quick calculations, and if this beam were to be designed out of reinforced concrete, it would weigh in the about over 1,000 pounds, and the box is only about 100 pounds. But ignoring the weight of the beam, let's proceed. So that's what's in there, and what I was normally going to do is say, and there's the weight of the beam. But that's inside the green loop. But we're not going to put that in there. Just not a realistic problem. Okay, then we'll put in the things we cut through. So we cut through the rope here. A tension of 791 kilonewtons. We cut through the rope here, a tension of 791 kilonewtons, and we cut through the wall, and in the wall there's a vertical reaction, a horizontal reaction, and a moment reaction. So I'm going to say M, Ry, and Rx. And we're given that the dimension from the wall to the center of the pulley is 4 meters. We're not given the radius of the pulley, so we're not exactly sure where the ropes are hitting. However, it doesn't really matter, and this is why. So if you look at a free body diagram of the pulley now, so here's the pulley, and here's this, we'll just say T in general, and it's equal. And there's the reaction, and it's frictionless. And so the two tensions have to be the same, because if you take moments about the middle of the pulley, they have to be 0 to balance out. And also, if you take the bisecting angle, and this is a trick you should know for pulleys, can you see that the here's this vector here, the tension vector, I'm drawing the components right there on the line. Can you see that these two horizontal components, because we've bisected this to be theta and theta, that kind of looks like a dog now, the face of a dog. But these two yellow components are equal and opposite, which means that the reaction here has to be along this bisecting angle. It can't have a horizontal component, because the two horizontal components of the tension have canceled each other out. And in fact, it's going to be 2 times T cos theta. And so we can do that. And then when you put it all together, it's the same thing as this. Here we go. 2 T cos theta. And that's going to equal vector-wise to this. It's as if those original tensions were applied at the center of the pulley. So what we can do is this. Let me redraw the problem. Try to draw it a little nicer. We can redraw it with the 791, okay, as if it was going right through the middle of the pulley. And so this little thing here about the pulleys would have to have been something that you had learned in statics. And I can do another tutorial about pulleys and maybe catch you up on that. Okay, so here is the free body diagram. It's just as before, with the small difference in that I put the 791 forces going right through the center of the pulley, which is going to be important because we do know that dimension is 4 meters. Okay, and this one equals m times 0. There is no acceleration. The beam is not moving. Okay, so it becomes a statics problem, so that's easy. Sum fx equals 0. So you've got, take right positive, rx plus, and that angle, theta was 30 degrees, plus 791 cosine 30 degrees equals 0. You get Rx equals minus -685 newtons, which means it's, I guessed the wrong direction. It's actually going away, and then if you look at the picture, it's obvious the cables are pulling, so the reaction should be back into the wall. Okay, sum Fy equals 0. Up is positive, Ry minus 791 minus 791 sine 30 degrees equals 0. Ry equals 1,187 newtons up. And then finally, some moments about A is 0. We'll take counterclockwise as positive. So I drew in the moment counterclockwise, so that's positive, MA. Okay, the 791 vertical has a moment arm of 4 meters. And what I'm going to do is take the vertical component of the rope that's at 30 degrees, so 7191 times sine 30 degrees. And it also has a moment arm of 4 meters. Okay, so MA equals, if you do that, comes out to 4746 Newton meters. Counterclockwise.